We're not just going to learn about numbers today. We're actually going to build our entire number system from scratch, piece by piece. We're going to see why these numbers even exist in the first place.
So let's kick things off with a big question. How many numbers does it really take to explain, well, everything? The answer might surprise you because here's the thing. Our number system wasn't just found. Nope, it was invented, step by step, to solve very real problems that people were facing.
All right, so let's do it. Let's start at the very beginning with the most basic building blocks. We're going to see why we had to keep inventing more and more numbers as we went along.
The first numbers anyone ever used. We call them the natural numbers. They're super simple, really intuitive. They were made for one job, counting stuff. One sheep, 2 coconuts, 3 people. And for a really long time, that was enough. That's all we needed.
But, simple counting only gets you so far. What happens when you run into a problem like this one? If you only have the numbers 1, 2, 3, and up, there's literally no answer. The idea of nothing, it just didn't exist in the numbers. It was a huge hole in the system.
And so, to plug that hole, humanity came up with one of the most brilliant inventions, ever, the number 0. It's wild to think about, right? With just that one new idea, we created what we call the whole numbers, and suddenly we could actually talk about the concept of nothing, or none.
Okay, so problem solved, right? Well, not so fast. Another problem pops up almost immediately. Whole numbers are great, but they totally fall apart when you're talking about something like debt. The moment you try to subtract a bigger number from a smaller one, boom, you hit a wall. Again, there's just no number in our system to describe that.
So what do? We invented something new again. This time, negative numbers. By giving every positive number a negative twin and opposite, we created the integers. And now, wow, we can suddenly talk about debt, or temperatures below freezing, or even direction. Our little number line just exploded, stretching out infinitely in both directions.
And at this point, it really feels like we're done, doesn't it? We can go positive, we can go negative, we've got 0 right in the middle, we're set. But what about sharing? What happens when you try to divide things? The integer system, it has no answer for 1 divided by 2. It's not 0, it's not 1, it's stuck somewhere in that gap in between.
And that brings us to the hero of today's story, rational numbers. So what are they? A rational number is just any number that you can write as a fraction, a ratio of 2 integers. And this was the huge breakthrough we needed to finally fill in all those infinite little gaps between the whole numbers.
And this idea completely changes everything. Suddenly, the number line isn't just a bunch of separate steps anymore. With rational numbers, it becomes this dense, continuous path. It's amazing, really. No matter how close 2 numbers are, you can always find another rational number squeezed in between them. The gaps are gone.
Okay, so we've built our set of numbers. We've got the whole gang here. Now we need to figure out the rules of the road. How do these numbers play together? Let's start with addition and check out the fundamental laws that make it all work so smoothly.
I like to think of these as the laws of physics for addition. They're just always true, which is what makes math so reliable. You've got closure, which just means if you add 2 rational numbers, you get another rational number. Simple. Then commutative and associative, those are the ones that give us all the flexibility to move things around. And finally, identity and inverse. They give us our home base, which is 0, and a way to get back to it.
Take the commutative property, for instance. All it means is that the order you add stuff in just doesn't matter. You can see right here, it doesn't matter if you do the negative fraction plus the positive one or the other way around. You get the exact same answer. That one little rule makes life so much easier.
But, okay, now for a plot twist. We all tend to think of subtraction as addition's twin, right? But when you look at these fundamental laws, nope, subtraction is more like the rebellious cousin who refuses to play by the rules.
And this shows it perfectly. Look, we take the exact same 2 numbers, but this time we subtract. Now, all of a sudden, the order is everything. One way, you get a negative answer. Flip it around, and you get a positive answer. 2 totally different results. So yeah, subtraction is not commutative, not at all.
So here's the bottom line, all laid out. Look at addition. It gets a nice happy check mark for all 5 properties. It's solid, it's flexible, but subtraction, oh man, it fails on almost every single one. Sure, it has closure, but that's it. No flexibility with order or grouping, no real identity, no inverse. It's just a way more rigid, rule-bound operation.
So, if subtraction is the weird one, what's the deal with multiplication and division? Well, I've got good news. multiplication brings back all of those elegant, reliable, and friendly rules that we loved about addition.
But before we can really talk about division, we have to get this one key idea for multiplication. It's called the multiplicative inverse, but pretty much everyone just calls it the reciprocal. All it is the flipped version of a fraction.
And here's the magic trick. Any number, any rational number, when you multiply it by its own reciprocal, the answer is always 1. That might sound simple, but it gives us an incredibly powerful tool.
Honestly, the absolute best way to think about this is like an undo button for multiplication. If you multiply by 5, you can just multiply by its reciprocal, 1/5, to undo it and get right back to the neutral starting point of 1.
And this is so cool because it leads to this amazing simplification. Are you ready for this? There really is no such thing as division. It's not a real thing. It's just a shortcut. When we say we're dividing by a number, what we're really doing is multiplying by its undo button. It's reciprocal, and thinking about it that way makes all the math so much cleaner.
Okay, I know, we've been going through a bunch of these abstract-sounding properties, and you might be thinking, so what? Why do I care if something is commutative? Well, here's why it matters. Knowing these rules is like having a mathematical cheat code. It's a superpower. Okay, check out this problem. At first glance, it looks like a total mess, right? Different denominators everywhere. But since we know addition is both commutative and associative, we can use our cheat code. We can just shuffle the numbers around, move them wherever we want, and group them differently. So let's put the fractions with the same denominators together. And just like that, a really messy problem turns into two super simple ones. We can solve it in our heads. That's the power of knowing these rules.
So think about the journey we just took. We started with just basic counting. Then we had to invent zero, then negative numbers, and finally all those fractions to build this incredibly powerful, dense number line. It really seems like we filled in every possible gap, right? But I want to leave you with a final thought. A question. Is the number line really complete?